receiver model. So the idea is now that we have a mathematical model, I make a step towards describing excess heat with it. Namely, if I can chop up a big quantum, now can I put this model together to have something to do with D2 going helium-4? So the simplest thing to do is if I had D2 and going helium-4, and if it fractionated the quantum, it gave the energy to the vibrational mode. That would be the simplest thing. That would be elegant. So I proposed this and calculated it out. And it turns out it doesn't work at all. And the reason it doesn't work at all is that two deuterons try to come together. There's a Coulomb repulsion between them, so the coupling strength is diddly squat. I need strong coupling. I get weak coupling. So this model breaks. I didn't know this model was probably model 152 or something. So this one didn't work. So the brainstorm back around 2001, 2002 was to introduce another transition. So I'm going to have my D2 to helium-4 be a really weak transition, and it's going to exchange an oscillator quantum. And over here, I'm going to have something else. I don't know what it is. I mean, in 2001, 2002, I had no idea what it was. So I said, let's assume I have a transition that's very strongly coupled now. So the energy starts here. I make the transition. The energy is given to this system, but this system now is strongly coupled. So this guy could take the big one and go slice and dice and chop it up and give it to the oscillator. So qualitatively, this model seemed to have a lot to do with what the experiment was doing. So in the excess heat experiments, the experimental evidence seems to be consistent with the picture where you go from D2 to helium-4. There's no observable commensurate energetic particles, which means you're not having normal nuclear reactions going on. In this scheme, the energy is given to another system that's chopping things up. The model, the described mathematical model, chops things up nicely, and the energy ends up in the phonon mode in this picture. So this model's, it's sort of the simplest model. And as a Hamiltonian, this probably looks like a mess, but in a sense, it's really simple. I got two-level system for the donor system, two-level system for the receiver system. Got my oscillator, I got loss, and I get linear coupling, weak coupling, strong coupling. If you like, this was proposed as being the simplest possible model capable mathematically of doing what the experiment was doing. So there you have it. As it turns out, there's lots of interesting things about this model. So we can analyze it, and the analysis basically works the way one might think intuitively, that for the weakly coupled system, basically if the strongly coupled system's able to fractionate the quantum, the weakly coupled system just gives the energy of the strongly coupled system and it makes its transitions. And the rate at which it does it is 4 times this thing, which is basically the rate at which it would happen if all the energy were matched perfectly. The donor quantum were perfectly matched to the oscillator quantum, you get this. And this complicated looking thing here is what the receiver system does. Basically what this says is that the coupling's not strong enough, it doesn't work. If the resonance isn't good enough, it doesn't work. But if you get everything right, then it works fine. And here's actually, from years ago, a toy calculation where I took some models where I was actually able to calculate absolutely everything by brute force numerically. So I calculated a couple, and I calculated the overlap matrix element. Turns out this is actually quite interesting. So in this case, the system that fractionates things has got a fractionated 151 quanta. So if the donor has 151 quanta, then I get this peak, and everybody's matched and everybody's perfect. If the donor's got a different energy over here, then the resonance is no good and it doesn't work. But I'm looking here, suppose just for kicks that the donor had like 300 quanta rather than 151 quanta, 302, then I'm up here. I got another resonance. So I'm scratching my head saying, why in the world do I have another resonance? Well, what's going on is my donor is this big, my fractionator receiver is this big, and if this excites two of them, and then it fractionates, that's what this guy's doing. And over here, this guy says, well, now I'm going to excite 10 of them, and then each one individually is going to chunk it up. So in this model, it describes not just fractionation, it has a subdivision effect too, which is like really interesting. And for my nickel, if you like, I think the experiments actually work that way. I mean, we're a long way between here and there, but there's gamma emission produced, and the gamma emission produced seems to be consistent with this kind of picture. Non-trivial result. This is actually a non-trivial result for a lot of reasons. So the new model says weakly coupled system, strongly coupled system, D2 to helium-4. All you have to do is have another transition that chops up the quanta. If you do that, you find the reaction rate is linear in the coupling matrix element. You might say, linear coupling matrix element. What's that mean? Translate that into English, please. Well, basically, coherent processes can have much faster rates than incoherent processes. So normal DD fusion is incoherent. This model describes a coherent process, which is orders and orders of magnitude faster. And along those lines, the tunneling factor that we described in the first lecture for hydrogen or for molecular D2 is a very small number. And if you have fusion, this number comes in squared, so it comes in and beats you overhead by 70 orders of magnitude. But for a coherent process, it only beats you overhead by 35 orders of magnitude. So if you like a coherent reaction, a coherent process involving two Ds making helium-4, has the possibility of being like 35 orders of magnitude faster without even doing anything to start out with. And in terms of competition with the incoherent reactions, the 3+1 reactions would see this factor, so they would be occurring at orders and orders of magnitude slower rate than this primary coherent process. So if you like, this constitutes an explanation for how to overcome the Coulomb barrier. You don't overcome the Coulomb barrier. You live with the Coulomb barrier. You're happy with the Coulomb barrier. It's just it comes in differently in this problem than it does for normal fusion reactions. If you take this model and you make estimates for the D2 to helium-4 transition, and you use those estimates to take this model and say, well, if the receiver can fractionate the quantum, how fast can the energy go? You end up out of the box with numbers which are in the range of what's experimentally observed. And that's interesting. That's really interesting. Takeaway message. We introduced donor and receiver model to deal with the weak transition problem. Analyze the resulting model. It looks like it works as a mathematical model just fine. The rates linear in the matrix element, which is a big deal as I've been talking about. On this slide, I explained that this is an explanation for Heisenberg's first miracle. Well, it turns out it's also an explanation for Heisenberg's second miracle, third miracle. And this model, out of the box, if you like, answers the three miracles, sort of just in the creation of the model itself. And the theory, this toy mathematical model, seems to be very closely related to experiment. Let me take away a message. Let me pause for thoughts or comments or questions. No thoughts or comments or questions. All right. Too late. No, I'm sorry. Go ahead.
Have any experiments been done specifically to test aspects of the model?
Actually, over the years, I would go to my friends at SRI and say, well, I tried this, can you try that? And in some cases, they tried this and they tried that. And most of the time, nothing would happen. And finally, something did happen, but it was the opposite of what was expected. But this is years and years ago, back when there were some resources and we actually could test things. But in recent times, there hasn't been much. But the rest of today's talk is actually going to be on exactly that point. So I appreciate your question. Okay, I was presenting all this stuff at some lectures at the international conferences, and one of my colleagues, Akito Takahashi, he got up and he said, you know, the curves that you're presenting, they go one way, but they go the other way. So, for example, if you start with the energy in the D2 and it goes into phonons, well, that seems to be something that maybe would be plausible. But your curves say it's coherent, so it could go the other way on equal footing. So, but if you start with the phonons, you could turn helium-4 into D2. And because your model says that, you know, I don't believe it's totally broken. It's baloney. And you know, my explanation to it at the time was, well, you know, if you do a little bit more sophisticated model, that you add dissipation of the oscillator quanta, then the oscillator has trouble giving the energy back because it has to lose the energy. Rates go down and so forth. So the model for fusion is free of that. But if you like, Takahashi was actually right. He had a good point. That these models say that you should be able to go from vibrational energy and get the energy back to the nuclei. And I was thinking, I thought, well, you know, that would be really interesting. If we could go the other way, then that would prove that this bit of physics can work, and then we could be sure. So, for example, the model was developed initially for going from donor energy to oscillator energy. But can we go the other way? Can we start with an excited oscillator and give the energy to a two-level system, give it to a nucleon? Can we excite nuclei with the vibrational excitation? And the model would say, why not? That's what the model does. It converts, it exchanges energy between systems with mismatched quanta, and it provides a mechanism to fractionate or to build up the quantum. Okay, those of you who know some physics, probably you've recognized already that this is a big deal. That if this is true, then it's something you need to know about. And if people were betting on it, they'd bet that probably it's not going to work. One of my friends said, no chance. The chances of that working, 1 part in a million. And my response was, oh, you're an optimist. Okay, but can it be demonstrated? So we've laid it out. We're going to roll up our sleeves and start trying to apply scientific methods to this and see what we can do. The model predicts coherent energy exchange. The two-level systems can be atoms, molecules, nuclei, spin systems. So strictly speaking, it doesn't have to be vibrations to nuclei. It could be like more accessible systems, and we could still demonstrate the effect in principle. And the oscillator can be like basically anything that oscillates. So there's a very large number of possibilities to show the effect. What I'm going to talk about today, and in previous years we actually spent a lot of time thinking about microwave to optical schemes and spin systems. For example, there's a community of people that are doing quantum computation, working with nuclear spins, and electronic spins, and oscillator to spin systems things, and those systems could be used for this kind of demonstration also. But I want to focus now on vibrations in the nucleon. Now, since I want to...
One thing I think your assumption is the other way you go, you have the system is linear. I mean, the system responds there's no material problem. But when you get all the energy focused on a certain region, you're going to have material breakdown.
It's not an energy focus kind of thing. It's more subtle than that.
Because
It's a transition happening again and again and again. Nowhere in any of this model do you actually want to have a localization of energy in the vicinity of something.
you're still talking about a couple MeVs. When you have those couple MeVs in the system.
I'm actually going to be talking about kilovolts now for this example. Yeah, well, hold on. Just let's follow me a few more steps, and we'll come back to it. Okay, since we're proposing something that's like the hardest thing in the world to imagine happening, probably the first thing to do is to try to take some steps to make life easy. And to make life easy, if we're going to transfer energy from vibrations to nuclear excitation, maybe we should start out by finding the nucleus that has the lowest transition energy for excitation among all the nuclei. So I started out in a big book, Letter and Shirley, and I flipped through and looked at every single diagram for the nuclear structures, trying to find the lowest energy transition. And at some point I said, well, why not use the databases? So there's NewDAP2 database. So you can log in, you can type in, find me transitions in this energy range, and it says, find me the lowest ones for all the stable nuclei or isotopes. And here they are. So the lowest energy transition is in mercury 201, 1.56 keV. The next lowest among stable nuclei is tantalum 181, and that's up at 6. So it's sort of like 4 times higher energy. So what do you think? Why don't we focus on the mercury transition? Because if it's hard to do in mercury, it'll be like harder in tantalum and harder. This iron transition is the famous Moskauer 14 keV long transition. So this will be like 10 times harder than that, or some power of 10, some multiple of that. So we've got a transition to focus on. I want to see if I can get some vibrational energy into this mercury 201 line. So this is the optimum candidate. Mind you, if you're willing to work with unstable nuclei, there's a transition in thorium, I think it's 221. It's 7.5 electron volts, which would be better in the sense that it'd be even easier than this mercury 201 transition. So we're recalling that the way things work is we need, this thing says we want lots and lots of vibrations. Actually, I'm not, let's see. Point of view has changed. When I made up these photographs, I was thinking donor receiver model. So if you like, I'm thinking of this formula is now going to apply to the 15 kilovolt 1.5 kV transition. And then I'm going to have another transition chop up the quanta, which is going to be different from what we're going to be talking about shortly. But when I think about a donor receiver, there's going to be some strongly coupled system that's going to do my fractionation or multi-quantum buildup for me. And this will be the transition associated with the mercury. So now we have a model for the system. Turns out I can estimate the overlap. I can actually do a rational design. And if you like, I've done a rational design, and I'll be talking about the results. There's several things that are interesting about it. That according to the model, if you succeed in doing it, then if you like, you have to have the coupling strong enough to give the energy to the nucleus. But that same coupling says that if you have a transition from an upper state to a lower state, like to radiate, that's going to have an associated line shape, which is going to be very broad. So the model says that if it can happen at all, it's going to have a broad line shape. The same physics which gives the energy to the nucleus broadens it. So if you like it, the way to think about it is if you vibrate too weak, then you get a little tiny bit of excitation, and the line shape's very narrow. Then if you hit it really hard and the vibrations are really strong, then you can get energy to the nuclear state, and the associated line shapes get ridiculously broad. So that's what it is that this version of the calculation says. So now I'm thinking about the system design. So it turns out I tried lots of different designs, and the basic design would say put mercury into a sample, put a vibrational source here. So I have my Acme terahertz vibration source. Most of you who are a little older probably know what the Acme refers to. Same with a coyote and a roadrunner. So if you vibrate the system and if you transfer the energy, then if the vibration is uniform over the sample, the energy transfers in phase. If the energy transfers in phase, then you get phased array emission. You would expect a collimated beam out. And that would be one of the characteristics of this demonstration, this experiment. That would be a way that you would know that you'd actually done it. I mean, getting X-rays out at all, isotropic would be exciting and interesting. But in this particular case, if you transfer the energy and you get your dipoles along the phase, you get collimated radiation out. And you can be, if you ever can see that, you'll be absolutely sure that you've done it. So we considered a lot of different designs, a lot of different transitions for doing the coupling. And if you like, you need a coupling between vibrations and excited state transitions. So I considered electronic transitions, like K-shell transitions, as being a source of the transition I could do my fractionating. And I considered nuclear transitions as well. So for example, I looked at K-shell to outer shell transitions basically in all the atoms as a possible candidate for a transition that could do the fractionation. So this would be an example of a strongly coupled transition, K-shell to outer shell. If you like, it couples the phonons because if you're in the lattice and you're vibrating, well, the outer shells notice whether the neighbors have moved or not. So the takeaway message, model predicts that we ought to be able to convert vibrations to nuclear excitation. 201 mercury's got the lowest transition energy. We get collimated X-ray emission if I could do it. The line shape will be very broad. And again, I actually plugged in all the numbers for this design. Basically, you get a meter system, you're driving it coherently, uniformly, systematically, terahertz as high frequency you possibly do, then you can get the thing to burp some X-rays according to the model. Take away message time for comments, thoughts, or questions. What do you think? But basically, the design is one which is sufficiently tough that it's going to be very hard to implement.
Has the experiment been done where you put vibrational energy into mercury with a terahertz vibrator?
You're willing to wait for another few graphics?
Okay.
You guys are getting out of the starting tank. I'll talk about the Karabut experiment. There's Karabut. Actually, it's Karabut in better years in times past. So Alexander Karabut is the Luch Institute. Karabut himself is an expert on low discharge technology. I went to visit him in his lab in the Moscow region, and I noticed all kinds of things. I was going in there, and there were guards with machine guns checking the IDs of the Russians that are going in one by one, looking at them, guns pointed at them. And my friends and I come by, and the guards are looking and they've got their machine guns. He says, Amerikansky, Amerikansky. He says, oh, come on. But in vicissitude, they have laboratories where they did glow discharges, and they have a 40-year history of doing research on glow discharges. You might say, but when's the last time glow discharges were hot in this country? 1930s, 1940s? Well, they continued working on them there, and they know more about glow discharges than anybody else in the planet. So Karabut is an experimentalist who's a real whiz with glow discharges. I visited his lab before the experiment we were talking about. So he shows up. I was the co-chair of the conference ICCF 10. It was held at the Sonesta just down the street from MIT. And Karabut popped up and he says, I've demonstrated an X-ray laser. Well, for those of you who know my history, I used to work on X-ray lasers. In fact, I invented X-ray lasers. Right? So I did. No, I was co-inventor. So Karabut was working with glow discharge. He observed collimated X-ray radiation at 1.5 keV. And by my assessment, there's no way in the world that you can an X-ray laser there. There must be some alternate explanation. And well, you've guessed what the alternate explanation is, what it is that I was designing. Karabut actually did. And in a sense, this is where Karabut's experiment and the theoretical ideas sort of were doing independently, and they came together and they crossed. Here's the experiment. We've got a glow discharge here. Down here is the cathode. Here's the anode. And there's low density gas here. And in this low density gas, the anode being an anode, the electrons are going that way, the ions are going this way. The X-rays come out collimated normal to the orientation of the cathode. Seems to work with, like, pick your cathode material. And it seems to work with, well, pick your gas material as well. I mean, he did extensive experiments with palladium and deuterium, looking for excess heat, and looking for neutron emission, transmutation, all kinds of things. And in other experiments, he claims to see a fair amount of excess heat in these experiments. And there's the very beginnings of a confirmation. Somebody reported like 1%, 1 or 2% anomaly potentially being the beginning of confirmation. Karabut reports 100% excess heat. Now let me see. The X-rays that come off, they're bright enough that you can use a pinhole camera to image the X-rays. So the beam comes up, he's got a small hole, and behind the hole he's got film. And here's the image, and he's imaging the cathode. So here's the size of the cathode, and the X-rays as imaged directly in the pinhole microscope, the pinhole camera here, is seeing emission, and that's sort of looking like the surface of the cathode, and it's a little bit brighter in the middle. And the way it works is sort of like this. Okay, this is the current, the discharge current. And it starts out, it turns the discharge current on. Now this is 100 milliamps here. And in a sense, this is high current regime. He's not got very much gas in there. So he's got a very intense glow discharge. That's one of the characteristics of Karabut's work. So discharge is on, no collimated X-rays. He turns the discharge off. Now, in connection with his turning the discharge off, his driving electronics is like, I was going to say Russian design, but that's not really right. Coulomb, of course. But when I went to visit with him in his lab in years earlier, one of the things we were interested in was current spikes and voltage spikes. He was seeing very short current spikes and voltage spikes with voltages, hundreds of keV, and duration nanosecond, sub-nanosecond. And I wanted to learn more about the diagnostics and what they were doing. So So here, when he turns this discharge off,